Welcome students. So today we are going to discuss about homogeneous differential equations with constant coefficients. So what is a second order differential equation? So the general form of second order differential equation is given by d square y by dt square equals to f of t y and say dy by dt. And the second order comes because of the fact that you have d square y by dt square. Now, when is this second order differential equation linear? It is linear if can be written as y double prime plus p of t y prime plus q of t y equals to g of t. Or you can have some p of t y double prime plus q of t y prime plus r of t equals to g of t. And otherwise it is non-linear. Okay. Now, typically when you have second order differential equation, you are to find unique solution or to find the solution. Typically there are two initial values or initial conditions given. Namely, y of t0 is some value y naught and y prime of t0 is some other value. We just choose to call it as y naught prime, just as a notation. This is not derivative of y naught. Y naught is a constant. So derivative of that is 0, right? So it's not, this is not same as derivative of y naught. Yeah, so loosely speaking, why do we need two constants? So loosely speaking, two conditions are required. Because two integrations, right? You'll integrate somehow from y double prime, you will use integration to get y prime, and then there will be another integration involved, which will give you from y prime to y. So because two integrations are involved, two integrations lead to two arbitrary constant, lead to two arbitrary constant. The proper scientific way to or mathematical way to look at that is that your null space, your differential equation, if you look at the differential equation as a linear operator, the null space of it is two-dimensional. And that is why you have two variables arising. Loosely speaking, again, you can make that theory more precise. Now, a second order differential equation is homogeneous if, so here there's a y missing, let me write that, if either this is 0 or this is 0, right? So if it is of this form, then g of t, small g of t is 0. If it is of this form, then capital G of t must be 0. So if g of t is a 0 function, or capital G of t is 0 for all t, otherwise for all t in R and it's otherwise non-homogeneous. Okay. So that's the idea. So for homogeneous or homogeneous differential equation, you see that there are two constants which come out naturally. Two initial condition must be given to you because the null space of a second order homogeneous differential equation is two-dimensional. Okay. Okay. Now let's look at one example. So suppose you're given this second order differential equation. Why is it second order? Second order because of this, and homogeneous because this is 0, and why, and what else? This is linear. Linear, and the coefficients are constant, right? So now recall, we have seen the solutions are formed. So if you look at y prime equals to ky, so recall has an exponential function as a solution, right? We already know what function that would be. That would be kt equals to y. So we will try. So try y of t equals to e to the power rt as a solution. So substitute into the differential equation given above. What do we get? So what is y double prime of this? So here you have y prime is going to be r e to the rt, and y double prime equals to r square e to the power rt. So a lot of times in the differential equation game, if you can conjecture a solution, it's easy to check. And if we find two different kinds of solutions for second order quote unquote kind, you will basically see how that is good enough as finding all the solutions. Okay. So again, I'm speaking very vaguely, but we'll make it precise as the time as we go ahead. So let's move this values in the differential equation. We get what is the second derivative of that is going to be r square e to the power rt plus 5 r e to the power rt plus 6 e to the power rt equals to 0. This gives me r square plus 5r plus 6 e to the rt equals to 0. This would give me r square plus 5r plus 6 equals to 0, as e to the rt is not 0, right? So this will give me r plus 3 times r plus 2 equals to 0. This gives me r equals to -3 or r equals to -2. And we have discovered, so there are two solutions discovered are y equals to e to the power -3t, putting it back in this form here, or y equals to e to the power -3t. Okay, so let's call this as y1, let's call this as y2. So these are the two solutions. Now, so we had a conjecture and we tried this and it worked out. Now, are these the only solutions, or how does the general solution to this differential equation looks like, right? So these are the questions we should ask. So if you have y1 equals to this, then y equals to c1 y1 plus c2 y2 is also a solution. Also solution to above differential equation. Let's check it out. What are the c1, c2? So c1, c2 are arbitrary constants. So let's check it out whether this works or not. So again, let's take this equation here and substitute in the given differential equation here. Okay, so let's see. So we need what? We need y double prime plus 5y prime plus 6y. Now what is y double prime of this? So by linearity of the derivative, you will see that this is going to be double prime y1 plus c2 y2 double prime plus 5 c1 y prime y1 prime plus c2 y2 prime plus 6 c1 y1 plus c2 y2. Now I'm going to break it. I'm going to organize it in a way that I'll collect all the y1s and y2 separately and their primes. So first one can be seen as c1 y1 double prime, then collect this and collect this. So we get plus 5y prime y1 prime plus 6y1 plus c2 y2 double prime plus 5y2 prime plus 6y2. And now these are the solutions to the differential equation. So these are 0. So you get c1 times 0 plus c2 times 0, which is 0. So clearly, y equals to c1 y1 is also a solution. Later on, we'll show that not only c1 y1 plus c2 y2 is a solution, which you have already shown now is a solution, but this is a general solution. Yeah, so this is what we'll show later on when we discuss the linear independence and solutions using Vronsky, but we'll come to that later on. Now, let's do the following problem. So find the solution to the initial value problem, y double prime plus 5y prime plus 6y equals to 0, y of 0 is 0, y prime of 0 is 1. Again, so we are given two initial condition, again, because the differential equation is of second order. So from previous slide, we have y of t equals to c1 e to the power minus 2t plus c2 e to the power minus 3t is a solution. Now you are given initial condition so that we can pick up the unique solution. So let's substitute. So this would imply y of 0. On one hand it is 0. On the other hand we'll get what? c1 e to the power 0 plus c2 e to the power 0. So this implies c1 plus c2 equals to 0. Similarly, now what is my y prime? So I need to use y prime. So y prime is going to be minus 2 c1 e to the power minus 2t minus 3 c1 e to the power minus 3t Yeah. So therefore, y1 prime of 0, on one hand it is 1. On the other hand, when you put 0, you'll get minus 2c1 minus 3c2. Nobody corrected, so c2, c2. So now if we solve these two equations, so equation 1 and equation 2, so substitute this, solve these equations together. So how do I solve it? I can take this equation multiplied by 2, so I get 2c1 plus 2c2 equals to 0, and this is equal to 1, by the way, right? So when you add them up, what do you get? You get minus c2 equals to 1. So this implies c2 equals to minus 1, and when you put this in this equation, you'll get c1 equals to 1. So therefore, the solution to IVP, the initial value problem, is y of t equals to e to the power minus 2t. For c1 we have 1, and for c2 we have minus 1. So c2 is minus 1. So I have c2 is minus 1 e to the power minus 3t. All right, so now once you have the solution, it makes sense to ask, is the solution unique, right? So for that, we'll have the discussion about existence and uniqueness of the solution again. So if you're given, so let's discuss the existence and uniqueness. So suppose you're given y double prime plus pty prime plus qty equals to g of t. So this is your second order differential equation, and it is linear. And along with that, you're given the initial conditions that y of t naught is y naught and y prime of t naught is y naught prime. As we discussed earlier, for second order, we need two initial conditions. So then this existence and uniqueness theorem tells us that if P, Q, and G, so if these coefficients here are continuous on an open interval containing T naught at the value where the initial T at which the Y values are defined and Y prime is defined, then this initial value problem has a unique solution pi of t which exists for all t in I. Now compare this with the first order linear differential equation. So in first order linear differential equation as well, you had unique solution on the whole interval where P, Q, and G are continuous, condition 1. Condition 2, where your T naught lies in it. Okay. So this is the existence and uniqueness. So although the solution is known to exist uniquely, and even though the differential equation is linear, there is no simple formula for this. Yeah. So this is a big difference between first order and second order. For first order linear differential equation, you had method of integrating factors, but here you do not have any of those kind of easy one-way setup, but we'll try to solve few of them. So let's look at the following problem. So find the interval where the solutions of IVP below is unique and continuous. Well, sorry, it's unique. So we have already seen the solution is what? So solution is y of t. So solution is, we have already seen this solution. This is the problem we have been working throughout, is e to the power minus 2t, e to the power minus 3t based on the initial condition. Here, what is my P of t? My P of t is 5, my Q of t is 6, and my G of t is 0. Yeah, what am I comparing it? I'm comparing it with, before I say what P and Q are, I'm comparing it with the following differential equation. Yeah. So now P and these are continuous These are constant functions, so these are continuous for all t in R. Therefore, the theorem of uniqueness, therefore, the theorem tells us, the above theorem guarantees unique solution for all t in R, or all t belonging to negative infinity to infinity, okay, on this interval. Let's look at the next problem. Determine the interval where the solution of the following initial value problem is unique. Now, before I go further, first thing I need to check is, does it satisfies the theorem? Because I'm going to apply the theorem. So first of all, is it linear? Look at the coefficients. Yes, so it is second order and linear differential equation. And this makes it homogeneous, but not needed, right? And like our theorem does not need this to be homogeneous, or so therefore we won't care about that part. Now let's convert this. So first, step one, convert this differential equation into standard form. Now, what is the standard form? Standard form means it should look like this. So y prime, y double prime has no coefficient. So let's divide throughout by t square minus 3t. So we get y double prime plus t upon t square minus 3t times y prime plus t, sorry, my bad, minus t plus 3 divided by t square minus 3t y equals to 0. Now we have, so what do we get? P of t and q of t. So P of t is t upon t square minus 3t, and q of t is t plus 3 upon t square minus 3t with a minus sign. And what is it? What is g of t? G of t is 0. So now P of t is continuous on, now when does it continuous? So it's continuous on, it's a rational function. Rational functions are continuous on their domain. So it's continuous on R except at t equals to 0 and t equals to 3. Similarly for this guy also, it's continuous on R except for t equals to 0 and t equals to 3. G of t is continuous everywhere. So what are the intervals we have gotten? The intervals we have gotten are 0, 3. And if you consider each individual interval, then the function is continuous. So there are three possibilities for the interval. 1, 2, and 3. Yeah, so there are three possibilities for interval. There are three possibilities for interval. Minus infinity to 0, 0 to 3, and 3 to infinity. However, you have to see where does your initial values for lie. So for our initial values are you have to see where, for what value of t is your initial value defined. So for what value of t, initial values are for t naught equals to 1. Thus, the interval is this interval here, right? 0 to 3, because that's where your 1 lies. So this is the idea behind the linear second order differential equations. Thank you for your attention.